From this slide, we will start to see Gauss-Jordan method. This is an alternative method to Gauss elimination. Actually, it's a variation of the Gauss elimination. Similar idea exists, but there is some differences. The major difference is that when an unknown is eliminated in the Gauss-Jordan method, it is eliminated from all other equations rather than just the subsequent ones. So if you remember, in the Gauss elimination, we were just eliminating these. And keeping this as the first term, then eliminating these. But in Gauss-Jordan, we are not only eliminating these, we are also eliminating this, and this to be able to have a diagonal matrix actually. All rows are normalized also by dividing them by their pivot elements. So we will have the normalization in Gauss-Jordan method. And therefore, the elimination step results in an identity matrix rather than a triangular matrix. You can see, as we mentioned, we eliminate all the values except the diagonals. We will have an identity matrix. Consequently, it is not necessary to employ back substitution to obtain the solution, because at each equation we will have only one unknown. And that's why from the third one we can calculate this, from the second one we can calculate x2 and x1 from the first one easily. In this slide you can see the algorithm or pseudocode for the Gauss-Jordan method. Basically the idea is similar to the Gauss elimination, but we will have this operation here, aug divided by d, and d is also aug. Actually, aug is the kk, the diagonal value you can think of. And with this, we will have this subtraction, and finally we will have the result. So this Gauss-Jordan has about 50% more operations than the Gauss elimination. The reason is that the actually eliminations will be done not only for the certain element but for all elements. That's why we have more operation. And the Gauss elimination is the simple elimination method of preference for obtaining solutions of linear algebraic equations. So actually, because there is a 50% increase in the Gauss-Jordan, using Gauss elimination is more efficient, we can say. But Gauss-Jordan is still used because it is used in engineering as well as in some numerical algorithms, because there is no back substitution. That's an advantage. You don't need to use back substitution and just use elimination in the Gauss-Jordan. In this slide, we will solve an example for the implementation of the Gauss-Jordan method. This is actually the same example that we solved in example 9.5 for Gauss elimination method. And let's solve this using the Gauss-Jordan method. So first we need to have the A matrix. Here you can see. And we can just write the A matrix and B matrix together in one common matrix actually. Let's write it down here. So like this: 3, 0.1, 0.3, minus 0.1, 7, 0.2, minus 0.2, minus 0.2, minus 0.3, 10, 7.85, minus 19.3, 71.4. So this is B, and these are A actually, and we write them together. Let's normalize, because in Gauss-Jordan we will normalize first this equation. So in the first term, actually for normalization we will just consider the A part, and here you can see the largest is 3, so we will normalize by 3, which becomes 1 minus 0.033333. 6 of them we can write as the book says, and minus 0.066667. And for B, it's again divided by 3, 2.61667. The others, so in the second one we will keep the others the same. Actually, we will just normalize the first first row, because it's also actually pivoted. This is like the largest is at the top. We don't need to do pivoting. Let's write the others as the same. 0.1, 7, minus 0.3, and 19.3. 0.3 minus 0.2, 10, 71.4. Now, we can eliminate x1 term by simply subtracting 0.1 times the first row from the second row, and also subtracting 0.3 times the first row from the third row. We can eliminate x1 from the third row as well. And if we eliminate them, I will not write these, but simply you can see that logic here. Maybe we can say 0.1 times and subtract from here. Also 0.3 times and subtract from here. Eventually, we will have just the elimination of the A11 actually, which gives us 1 minus 0.0333333 minus 0.066667. This is the same, and the remaining is here. We eliminated the first term, and this became 0.333 minus 0.293333 because we subtracted 0.1 times the first row from these. These will change. Minus 19.5617. And the third row as well, we subtracted 0.3 times the first row, and the first term was eliminated, and the remainings are minus 0.190000, 10.02000, like this, and 70.6150. So now what we need to do is simply we can also eliminate x2 from the first and the last row, because we want to keep this as the second row unknown is x2, and we need to eliminate this and this. To do that, we need to make some operations and eliminate them. When we make those operations, from here, let's say eliminate x2 from first and last row, first and third row. When we wanted to eliminate, the result is 1, 0, minus 0.068069, 2.52356, and 0, 1. Of course, we wanted to have actually this as 1, so maybe you can normalize this, then multiply this by this and subtract from this to have this value, then multiply this by this value after normalizing, then subtract that multiplication from the third row so that you can have 0 for the second unknown. So here 0.04188848 and minus 2.79320, and the third row is 0, 0, 10.01 200 70.0843. So after making this, normalize the third row again. So here we normalize this and multiply by this and this to subtract from here and here to obtain these. Now we need to normalize this. Normalize. Then multiply by this one and multiply this one and subtract from this, and also multiply by this one and subtract from this. Finally, we will have the result of, I will not show the intermediate operations, 1, 0, 0, 0, 1, 0, 0, 0, 1, and 3 minus 2.5 and 7. You can see actually we obtained the results, which means x1 is 3, x2 is minus 2.5, and x3 is 7. So this is x3, this is x2, this is x1 basically. And we obtain these. Simply, as you can see, we obtained an identity matrix which only has one unknowns at each row, so that we don't need any back substitution. We just simply say these are the results. So this is very straightforward and easy actually. By first normalizing, then multiplying by the certain row and subtract from it to eliminate the desired unknown, let's say, from the equation. So with this, we've actually completed the Gauss-Jordan method as well. We completed the section 9, which was about the solution of the systems of equations. We used Gauss elimination as well as Gauss-Jordan as the advanced methods. Also, we showed how to get the determinant and using Cramer's rule or elimination for the small number of equations, smaller than 3. But for the larger ones, we use Gauss elimination, which includes also pivoting and also scaling. Similarly for Gauss-Jordan, which is different because we have only one unknowns at each row in the end, and we applied normalization and also elimination only. We don't need any back substitution. So you can see these details from part 2 and section 9 in the book. The page numbers are here. You can, if you have further information, you can read these and have some further information. And thank you for your attention, and see you in the other sections.